We're in Chapter 7A, one sample t-tests, and we're going to do part 1, going over where we've been and where we're going. So where we've been on the z-test. We've been comparing a sample mean to a population with a known mean and a known standard deviation. Quick example. On average, happiness for human beings, our mean equals 5.5 and standard deviation equals 1.5. Ch07A thought people who hiked often would have higher happiness levels. She saw 9 hikers and asked them to rate their typical level of happiness, and the score for her hikers was 9. And we're quite familiar with how to parse the problem. We find we're measuring happiness in a one-tailed high test, comparing people who hike often with people in general. And of course, we have our 2 hypotheses stated. In this case, the HO, the null hypothesis, is stated first, and HA, the alternate hypothesis, is stated second. And in the same problem, we know how to describe the comparison distribution. The shape is normal, the z distribution in this case. The center, mu for the distribution of means, is the same as mu, and that's 5.5 stated in the problem. And we know the spread. We know when we have samples larger than 1, we have to use the distribution of means. And so sigma for the distribution of means is the square root of sigma divided by n. And sigma, standard deviation, is stated in the problem here. So we go ahead and calculate variance by squaring sigma, divide by n, and take the square root to get standard deviation for the distribution of means. So that's usually the longest step, and that's. So we knew that the next step in our process, step 3, we need to look up the cutoff point. You've used the calculator now many times to enter in alpha, and we have a one-tailed high test, and so doing that, you know that z alpha equals 1.64, and of course we would draw the lines in the appropriate places. So right here would be the cutoff point associated with alpha of 0.05. We'll write z alpha equals 1.64, and we know that the shaded region to the right side of the distribution is what we will call the reject region, meaning that we will reject the null hypothesis HO if the sample z-score lies in that area, and if the sample z-score lies in this center region, anywhere where it's right, we will fail to reject HO. So the next step is to calculate that z-score, which we do with the formula z equals m minus mu divided by the standard deviation for the distribution of means, coming up with a z-score of 3. And our last step, we decide and conclude our z-score of 3 is way up here. I can't even draw the flag. So let's write z equals 3. And since it is way into the tail of the distribution, we'll decide to reject the null hypothesis. The null hypothesis stated that there was no difference. When we reject it, all we're left with is the research hypothesis. And so we conclude that people who hike often have significantly higher levels of happiness than people in general. We write the concluding statement by writing z, and then we write the number right here. We type in the z-score and tell the probability level, the p-value. The probability of getting this kind of a score by chance is less than 5%. So that is the z-test. So now we're going to work a little bit with the t-test, which is a test that we use in a slightly different set of conditions. So in a one-sample t-test, in a nutshell, we're going to compare the mean scores from a sample, group drawn from a population, against a population with a known mean but an unknown standard deviation. As an example, consider this problem's study hours. You read an article in a college newsletter stating that students spend an average of 16 hours per week outside of class on coursework. You think to yourself, that can't be true. As a music major, you believe that music majors spent a lot more time than that because of all the practicing they have to do. And you want to test your hypothesis by comparing the coursework hours of 5 music majors to the average reported in the article. But there's a problem. You don't know the standard deviation of the comparison distribution, the students in general, so you only know the mean. So how do you know if music majors really do study more? So the solution to the problem of no standard deviation information is what we call the T distribution. And the T distribution is just a distribution of hypothetical scores used to define the comparison distribution in t-tests. So we'll take a close look at it moving forward, but you can see here what we'll talk about is the standard normal distribution. This taller, more normal-looking distribution, that's our Z distribution. And this is the T distribution in an example where there aren't very many individuals in the sample. So let's talk about it a little. So in what ways are they similar? So like the Z distribution, the T distribution is represented by a curved line. So both of them, we're going to draw it in the very same way with this curve. Like the Z distribution, the T distribution is a hypothetical distribution of an infinite number of samples of a particular size drawn from a population with means plotted onto a histogram. So it's the same concept that's used to make the Z distribution, but the only thing is that this time we're using all of those means and samples to also calculate the standard deviation, so we can find out if the variance is similar for each sample as it is to the main population. So the differences from the Z distribution, you can see that unlike the Z distribution, the heaviness of the tails of this distribution differs based on n-1. So you can see that in the T distribution, the one that's shorter, lower on the chart, we have this really fat tail. So there's going to be a lot of values in this tail. If we want to get just 2% of those values, we're going to have a pretty high Z-score. Unlike the Z distribution, we have to estimate the standard deviation using information we get from individuals in our sample. So once again, this T distribution I will talk more about on the next slide. So looking more at these two distributions. So on this chart, you can see the Z distribution, the standard normal distribution that we've been working with. On the top here, this blue kind of normal tall distribution, and that's what we've been working with all along. You can see that we have two T distributions here, and there are an infinite number of T distributions that we could draw, but we can see here that the shape is a little different. In both cases, the red and the green, you can see these heavier tails, more values in the tail of the distribution. So the reason that they're different is because a T distribution based on larger sample sizes greater than 30, has slightly fatter tails. So the cutoff points are going to be slightly more extreme. And a distribution like the green one, based on smaller sample sizes, has much fatter tails. So the cutoff points will be much more extreme. And so you can see here the n smaller than 30 with those very fat tails, the distribution close to 30, it's not that different from the normal, and it gets more normal the larger the sample size. So why does that produce a different cutoff point? Well, if you think about the fact that the cutoff point is related to the percent of scores in the tail of the distribution. Well, you can see that in the distribution like the green one above, if we're going to figure out where 2% of the values are, where there are quite a lot of values in this region. That's really big compared to the much thinner number of values, say, in the normal distribution, just this little bit. And so in order to accommodate just, say, 2% of the values, the cutoff point really does need to be quite a bit further into the tail. So maybe if we have this green distribution, the cutoff point has to be way out here in order that 2% or 5% or whatever we're deciding on is in the tail. So if you don't fully understand this from this explanation, don't worry. You can solve the problem without understanding this, and you'll wrap your head around it in time. So in a t-test, we estimate variance of the comparison distribution based on the sample. So we know certain things because of the work of mathematicians like this guy. We know that the variance from a sample provides a good but slightly biased estimate of the variance of the population. Excuse me. How do we know? Because mathematicians have done this task to find out. They've tested it by drawing huge numbers of samples from particular sizes from the population and then calculating the variance. And if they know what the variance actually is for the population, then they can know how closely each sample gets to allowing us to estimate the variance of the population. So that's kind of how we come to know that this is true. But bias is found. When we draw all of these samples and calculate out the variances, estimate based on the samples that we draw, we know that the variances are going to be just a little bit smaller than we actually find in the population. And so to correct that, there's an adjustment that we make. So we estimate variance for the population using a slightly different formula. We use this SS minus divided by n minus 1 instead of what we have been using before, SS divided by n. And this might not seem familiar to you anymore because we really haven't worked with SS since chapter 2. So we'll be reviewing the calculations for standard deviation in this chapter, and we'll be using this adjustment for finding the average of the sum of squares or for finding the variance. And by the way, a new term that you'll be using a lot is degrees of freedom, or we abbreviate it DF. And DF is just equal to n minus 1, with n being the number of participants in the sample. And that's what n equals. And that's a nice, easy math problem to do. So let's go back to the problem that we were working on with study hours. You read an article stating that students spend an average of 16 hours per week outside of class on coursework, and you think music majors have more hours because of all the practicing. So your hypothesis, music majors will spend more coursework hours outside of class than students in general, who spend on average 16 hours per week. And you're very familiar with how we parse the problem. We have population 1, the students who are music majors, and we'll compare them with students in general. We'll measure for our dependent variable coursework hours outside of class, and we'll use a one-tailed high test that we can indicate because of the word more in the problem. Our research hypothesis, H1 or HA, is that population 1 will spend more coursework hours outside of class than population 2. And our null hypothesis is that population 1 will not spend more coursework hours outside of class than population 2. So back to our problem. We're on step 2, and we can see we have some added information. We have the information added about the sample mean. And it says your sample of 5 music majors, that will be important, spends an average of 19 hours per week on coursework outside of class. And we're going to test with alpha equals 0.05. And of course, we've already been told about the 16 hours per week spent by a typical student. So we're going to describe the comparison distribution, and we do it the same as we have before. We know the center of the population 2 is going to be mu, and in this case it's 16. Students in general is always what the comparison distribution talks about, that general population. The shape, now we're using the t-distribution, but the big key word that we're always going to use in our class is normal. And that is not because it's always true, it's because it needs to be true. It's an assumption of any statistical test, but we are not in this class testing for normality. However, in the real world, we would assume normality under two conditions. If n is greater than 30, or population distribution, this 16 hours per week, is known to be normal. But you'll see that in your book. In our class, we're not going to worry about it, but just so you know it's there, you can continue to write the word normal. And now we come to spread, or how wide is this distribution, and that will take our little bit of calculating. And to do our calculating, we're going to be going back to something we haven't done since chapter 2. We're going to be calculating sum of squares. And so I'm just going to draw a line across here and put some headings, because you maybe will recall that the formula for sum of squares requires us to calculate deviation and standard deviation. So let's go ahead and pull out some key information from the problem before we calculate any information about the sample, about the population in general. So here is the information I can see right in the problem about our sample. I can see that n, the number in the sample, is these 5 music majors, so n equals 5. And I know that degrees of freedom we'll be using is going to be n minus 1, which equals 4. I can see the mean. I could calculate it, but we don't have to because it's already stated in the problem for us. In your problems, you might need to calculate it, but you know how to do that. And we will be calculating the sum of squares for our sample, and you might recall that the sum of squares is just the sum of each deviation, each score minus the mean squared, equals our sum of squares. So let's go ahead and get I'll write up here our deviations. I'll just abbreviate it. And we know that deviation means x minus m. So in other words, 15 is x minus the mean is 19 equals negative 4. 22 minus 19 is 3. 18 minus 19 is negative 1. 19 minus 19 is 0. And 21 minus 19 is 2. We have our deviations. Now we need to get our deviations squared, or x minus m squared. We've already calculated x minus m, so we'll just take negative 4 squared equals 16. 3 squared is 9. Negative 1 squared is 1. 0 squared is 0. And 2 squared is 4. If we sum up all of these deviations squared, we get the sum of squares. So let's go ahead and sum those up. And if we sum up the 16 plus the 9 plus the 1 plus the 0 plus the 4, we come up with 30. From here, we can continue on to get some inferences about the population, or the comparison distribution. So, for example, it's given in the problem that they spend an average of 16 hours per week. So we know mu equals 16. Now, we can't get the variance straight anymore, so we have to estimate the variance. So the estimated variance is simply the sum of squares divided by the degrees of freedom. So we used to take sum of squares and divide by the number in the sample, sort of taking like the average of the squared deviations, but now we're dividing by the degrees of freedom, which is 30 divided by 4, which equals 7.5. You'll notice that I put this little e in front. This is not conventional in mathematics. In class, you're going to be seeing this written as, we haven't even gotten here yet, s squared for variance. When you use an s instead of sd, that means it's been estimated. And so this is how it's going to be written in your book. But we're going to use EVAR because I think it's more clear. So this is the only thing that's different about calculating any of the standard deviation. We estimate the variance by dividing by degrees of freedom. Now we can go ahead, just as we did in the previous test, we can get the variance for the distribution of means by taking the estimated variance in this case and dividing by n. And this is exactly what we did in the z-test. And so that equals 7.5 divided by 5, which equals 1.5. And we're at our last step. We have to calculate the standard deviation. So because it's an estimated standard deviation, we just use this s instead of using the SD or the sigma sign. So S means we're estimating the standard deviation for the population, and we estimate by just taking the square root of varm, just as we did before, which is the square root of 1.5, which is 1.2247. And that is spread. Spread is going to be indicated as the standard deviation for the distribution of means. I forgot our little m here. For the distribution of means, which equals 1.2247. And this little accidental mark that I made doesn't belong, so just to avoid any confusion, I'm going to just erase that little mark right there. There we go. And so that is what we work as. One more point I'll make now, and I'll make it again later, is that we need to just be aware that these terms that I use, var and evar, technically this would be evarm2. In your book, you're going to see them as s squared m, not evarm. And so this is just something a little bit different that we do to make it a little easier for you. And this was the hardest thing you're going to do. Everything else is going to be the same. So we now continue with the last 3 steps of hypothesis testing. So we discover that when we look up the cutoff point, the process is the same, the cutoff point calculator is going to be the same, and we're still going to rely on whatever is the stated alpha in the problem and whatever we've identified in terms of the tails of the test. But for a t-test, we add one more piece of information. We add the degrees of freedom. And we'll have to enter this in when we look up the cutoff point score, the cutoff t-score. So we're going to enter in this 4 when we do it. I can't do that inside of PowerPoint, so I'll be showing you that in a separate video. I went ahead and looked it up for you, and I discovered that the t-score associated with alpha, or we might say the cutoff point, is 2.13. You can see that's quite a bit higher or more rigid than the z-score, which would have been 1.64. So here we go. Let's place our 2.13 cutoff point right about here. We'll label it as T alpha now because we're doing a t-test, and we'll put our 2.13. We can get out our highlighter and shade the tail of the distribution here so that we know where our reject region is, and we can still rely on all of this region in the center of the distribution for failing to reject our null hypothesis. We're done with step 3. Let's go on to step 4, which is calculating the sample t-score. And you'll see here that the formula for t, this should be lowercase, is the sample mean minus the population mean divided by spread. And if that looks familiar, it should, because it's exactly the same formula as calculating the z-score. In this case, we'll write it as t equals sample mean m, not forgetting parentheses, minus mu, divided by, and remember our symbol now for spread is just this s, indicating that we've estimated the standard deviation, and this little m, meaning that it's for the distribution of means, or that we took that last step of dividing variance by n before getting the square root of it for standard deviation. When we take this problem, we take our 19 for our sample mean minus the 16 for our population mean, and we divide it by our spread, which was 1.4, and let me get out my answer here, 1.2247, and I won't erase, I'll just write over here 1.2247, and we discover that our t-score is 2.4494, 2.45. We can now place our t-score within this grid, and we'll mark it with a red pen here. 2.45 is going to be further into the tail of the distribution, maybe right around here. T equals 2.45, which means that our decision, just like we make in other problems, is that we will reject the null hypothesis. It's not in the fail region, it's in the shaded region. And our conclusion is that students who are music majors have significantly more coursework hours outside class time than students in general. And we write our statistic the same as we did before with one little change. We write our statistic now as t, so we'll start with that. And then down here in the subtext, we don't write n anymore. We write degrees of freedom. Degrees of freedom equals 4, and then we continue on and write our t-score. So t equals 2.45, and then we tell the p-value the same as before. The probability of achieving a score, the number of hours this high by just a random sample drawn by chance, is greater than 0.05. I mean, it's less than 0.05. We have a less than 5% chance of drawing a random sample that has a t-score of 2.45. So what's the same between a one-sample t-test compared to the z-test? Well, both tests compare a sample mean to a known population mean. Both tests use one or two-tailed tests according to the hypothesis. Both tests require parsing the problem in just the same way. Both tests use the same formula to calculate the standardized sample score. And you can see what that is. In the z-test, it's sample mean minus population mean divided by spread. And the same is true in the t-test. Both tests use the distribution of means based on sample size. So we're still going to be going through that formula to calculate the distribution of means. And both tests look up cutoff points. So you'll be familiar with all those things. So what's different about the one-sample t-test when compared to the z-test? The standard deviation. In the z-test, the standard deviation is provided, but in the t-test, it's not known. We have to estimate the variance for population based on the sample. variance. Secondly, the cutoff point is going to be different. In the z-test, we used standard cutoff points based on the z-distribution. We looked those up, you'll remember. But in the t-test, we're still going to be looking up cutoff points, but we'll be using a t-distribution, and we'll be basing it on alpha and something called degrees of freedom. And thirdly, the standardized score, you already saw that it's the same, which it is. In both cases, z-score and t, it's sample mean minus population mean divided by spread. But the symbol for spread is going to be this thing called SM instead of sigma m, because we calculate it differently.